Hello, my name is Phi Hong. Today I will present our work named Fully Secure PSI by MPC-in-the-Head. This is the joint work with my advisor, Dr. Gordon and Dr. Carmit Hazay. First, I'd like to introduce the privacy intersection problem briefly. The PSI ideal functionality takes input from Alice and Bob. It has a setup size W. The functionality then computes the intersection between the two input sets and gives the output to Alice and Bob. In practice, the ideal functionality can be relaxed to allow some slackness, where an adversary may be able to use an effective input set of size W prime greater than the agreed upon W. PSI has many real-world applications. For example, it is used to compute private contact discovery, or when two companies want to identify a list of overlapping customers, or when two states want to find the common names in their blacklist. It is desirable that the PSI protocol is secure, and in many cases, all parties will receive correct output. PSI is an important problem and is studied extensively among the cryptographic community. Theoretically, this is an interesting and challenging mathematical problem. Practically, PSI is used as a subroutine in many important real-world applications. There is a long line of work in terms of PSI, both in two-party and multi-party setting. However, all existing work focus on the case where only one party will receive the output. Of course, the party receiving the output can relay it to other parties. However, doing so implies the use of expensive generalist proofs, and the protocol will be impractical. And one more point, most of the current two-party PSI protocols and multi-party PSI protocols are developed using different techniques, and the two PSI solutions do not extend to the multi-party setting. Recognizing the shortcoming in the PSI literature, our work aims at designing new fully secure PSI protocols in both two-party and multi-party settings. Our protocols are secure against malicious adversaries and provide the correct output to all parties if they ever receive any output. Our multi-party PSI protocol is built on top of the two-party PSI protocol. Our protocols are constructed based on the IPS compiler and use Leviosa as the blueprint. One interesting point about our protocols is that ours only need black box access to passively secure OLE, but achieving malicious security. Besides the new PSI constructions, we also improved the IPS compiler in multi-party setting. Before introducing our protocols, I'd like to go through the background work that our constructions are based on, which is the construction presented by Krishnan and Song. At a high level, Krishnan and Song encode the input set with the polynomial. Krishnan and Song prove that if the parties compute T equal to Q1R plus Q2S, where R and S are random polynomials, then T can be written as T equal to VW, where Vx encodes item in the intersection and W has uniformly random distribution. As a result, T preserves the intersection without leaking anything else. To make sure that R and S are chosen uniformly at random, each party samples a random share of the polynomials. As we can see here, all the blue polynomials are held by P1, while all the red ones are by P2. After computing T, each party evaluates T on their input set and outputs the intersection. With Krishnan and Song design in mind, GN19 proposed an effective way to compute Tx. GN19 reduced the computation of Tx to two Oblivious polynomial evaluation instances. Before going into the details of GN19 protocol, I'd like to note that the blue polynomials are entirely known by P1, while the red one are known by P2. Now, with the first OPE, P1 provides S1, where P2 provides Q2 and U2. Where U2 is a uniformly random polynomial, P1 will obtain T1 equal to Q2 S1 plus U2. With the second OPE, P2 obtains T2 equal to Q1 R2 plus U1. After obtaining T1 and T2 respectively, the parties use their local data to compute T1 hat and T2 hat. We can see that P1 only adds the blue polynomials to the equation, which is Q1 R1 minus U1, while P2 only adds the red ones, which is Q2 S2 minus U2. When adding T1 hat and T2 hat, Tx is recovered. The GN19 major contribution is to have a very efficient instantiation of OPE by the OLE. Consider the OPE computation where P1 provides Y, P2 provides A and B, where P1 will obtain C equal to A plus BY. First, both parties will agree on a set of 2W plus 1 random points, EI, where W is the degree of B and Y, and A has a degree of 2W. Let YI, AI, BI be the evaluation of Y, A, and B at the point EI. Then the two parties make an OAV call on the inputs YI, AI, BI, where P1 obtains CI equal to AI plus BI multiplied YI. After 2W plus 1 calls to the OLE, P1 can recover CX by interpolating the polynomial of degree 2W over the points EI and CI. With this approach, GN19 came up with a linear communication PSI protocol in semi-honest settings and a way to extend their protocol to multi-party settings. GN19 attempted to make their protocol secure against malicious adversaries, however, were not successful. And the question whether there's an efficient way to make GN19 malicious secure was still open. In this work, we give a yes answer to the previous question by providing new fully secure PSI protocols. Our protocols are secure against malicious adversaries and provide output to all parties. Our protocols start with GN19, and in order to achieve fully secure PSI protocols, we use the IPS compiler. Our two-party protocol uses Oblivious as the blueprint, and it is extensible to multi-party settings. Interestingly, we achieve fully secure properties almost for free, where our protocols are just a little bit more expensive than the semi-honest protocols proposed by GN19. Now, I'd like to give a short overview about the IPS compiler to give an intuition why the IPS compiler can help providing output to all parties. Assume n parties want to compute a function f on their input x1 to xm. With the IPS compiler, they will first secretly share their input and send the shares to an imaginary servers and run an MPC-in-the-Head protocol that computes f. The IPS compiler achieves security against malicious adversaries by the use of Watchlist mechanism. From the start of the execution, each party can select T random servers to watch. For the 1,000 servers, the party will have all the shares and randomness and can verify the computation from the beginning to the end, including the output. So if the function f provides output to all parties, each one can use its watchlist to verify the correctness of the output. Optimizing the IPS compiler for the privacy and the section problem, we construct very efficient two-party and multi-party PSI protocols. Our protocols are the first ones that provide output to all parties, so we can only compare it with existing one-side output PSI protocols. In terms of communication cost, our protocol has better communication complexity compared to other protocols. Our communication cost is dominated by MW kappa, where M is the number of parties, W is the input size, and kappa is the security parameter. We will show later that T is very small compared to W in our total cost. Now I'd like to go into the technical details of our protocols. First, I'll start with the two-party protocol. We follow Oblivious and IPS compiler closely in our construction. At the beginning, the parties have the polynomials Q1 and Q2 that encode the input set. As the input set size has size W, Q1 and Q2 have degree of W. The first step is to pack Q1 and Q2 with random polynomials T1 and T2. Each has degree T plus E, where T and E are the cut-and-choose parameters such that 1 minus T over N to the power E equal to 2 to minus lambda, where lambda is a security parameter. Next, the parties will secretly share Q1 TIL, Q2 TIL, R1, R2, S1, S2 to the imaginary servers, and each selects T random servers to watch. The shares are the evaluation of these polynomials on endpoints EI, or the resettlement code of the input polynomials. At each server, the parties compute the share Ti of the output polynomial Tx. The correctness of T is guaranteed by the watchlist. I've just gone through the high-level description of two-party PSI protocol. Now I'd like to talk about how we set up the watchlist for our MPC-in-the-Head in detail. The IPS compiler and Oblivious use TF and OT to set up the watchlist. Doing so, we incur the communication cost of ON, we replace the OT approach with the commit then review paradigm. Instead of quietly watching a live channel, the parties are asked to commit to their shares using a Merkle tree before the computation, and only when they perform a check after the messages are sent do they agree on a random set of T channels. The commit then review paradigm only needs OT log and communication cost, which is much better than ON. Next, we extend our two-party PSI protocol to the multi-party PSI protocol. Our multi-party PSI protocol used star topology as in HV17. We start with a semi-honest protocol and make it secure against malicious adversary by using the IPS compiler with a more efficient watchlist setup via commit then review paradigm. At a high level, we have a designated center party called P0. The party P0 and each PI performs a modified 2 PSI protocol. After each execution, P0 receives Q0 RI plus QI SI plus VI, where RI, SI, and VI are random polynomials. On top of that, VI is chosen by all the parties, such that the sum of all VI is 0. After the pairwise 2 PSI executions, P0 obtains the polynomial T that encodes the intersection of all the input sets. P0 will then send T to all other parties. The correctness is then enforced by the watchlist. Without our optimization, the watchlist setup will be very inefficient. As in IPS compiler, each party will have T shares learned by one other party. Altogether, M-1 shares can be learned by M-1 parties. In order to preserve privacy, the input polynomial needs to have a degree of at least M-1 T plus E. And the instantiation of the multi-party watchlist is very expensive. On the other hand, our commit then review paradigm works the same way as in the other two-party setting. The parties first commit to the shares and randomness for all the servers using the Merkle tree. After the execution, they will decide to get the T random servers to verify the computation. So the degree of the pattern polynomial is still T plus E, and the communication cost to commit then review is O and T log n, which is negligible overhead. Thank you.